This is a lesson on reflection and spherical mirrors in a unit on light and optics. In a prior lesson, I covered the law of reflection with reflective surfaces, and that'll still be true as we move into spherical mirrors. So many of those terms will come up again and be familiar in concept. So spherical mirrors are defined by the fact that they're characterized by a focal length. And the reflective surface is shaped as a portion of a sphere. Notice that the sphere doesn't have to have a very small radius as long as it's spherical in some matter. And what we see with a spherical mirror, as long as this is ground or created such as that it's a portion of a sphere, this light coming in, any light coming in parallel to each other, will come in, hit the spherical surface, and then reflect back to what we call the focus or focal point. And so each mirror is defined by its focal length, where all of the light rays coming in parallel will meet up at that point. Notice at the surface of all of these, where all of these rays reflect, we can see that the law of reflection is in effect. And you can see that all along here for each one of these rays. Any ray that hits a mirror follows the law of reflection. But with spherical mirrors, we make the task easier by knowing that there's specific light rays that come in that follow a very predicted path. And this is one of them. It comes in parallel and goes through the focal length. I don't have to do any calculation with any of these angles. I just know that's the path the ray follows. R here, when I look at the equation for the focal length, R is the radius of curvature. And then I also have a plus or minus here for the difference between a convex and a concave. Concave has a positive focal length and convex has a negative focal length. So that's why you see the positive or negative in this equation here. Concave and convex mirrors are named differently because they are shaped differently. They're both spherical mirrors, but one has the reflective surface on where the focus is on the same side as the light rays. And with a convex mirror, the focus is on the opposite side or behind the mirror compared to the light rays. So we can see the light rays come in all parallel. Right? Just like I was saying, they come in parallel, and all of the light rays that come in parallel will converge at the focal length. And so they're going to diverge on this side. All of these rays over here, they diverge in different directions, and they all follow the law of reflection. But what we know is they can all be traced back to this focal point. So we see that this is a positive focal length, and then this is a negative focal length behind it. We're going to use the focal length in calculating where we expect to find images due to objects. And we did that with flat mirrors. If there was an image, or if there was an object, we knew where to locate the image because we had an equation. With flat mirrors, it's easy. DI equals negative DO. But with concave and convex or spherical mirrors, here's the equation mathematically. It's much more complex. You can see that in here. Be careful when you use this equation that you're doing the algebra accurately on this. I see some students make the mistake of taking a negative sign where they should actually do a reciprocal. So watch out for that. So if you know the focal length and you know the object distance, you can find the image distance. And it's a very simple equation. We're going to use this equation for mirrors, spherical mirrors, and also lenses when we have simply ground lenses. The magnification of an image, and I had talked about this, you may be interested whether the object is larger or smaller, especially when you get to optical instruments. If a telescope or a microscope, you want to enlarge and be able to quantify that. And so we know magnification is sort of this relative, what's the height of the image compared to the height of the object? And this is by definition, this should make sense that we're taking a ratio of those two heights. It turns out that the ratio of those two heights is related to the image and object distance, which you can calculate with the mirror lens equation. It's negative DI over DO. What I'm going to note here is that your sketch should match your math and vice versa. I'm going to teach you how to draw some principal rays, right? We know there are some rays, and we can do a sketch to predict where the image is. And when I get the sketch, it should match the math that I do for calculating the image distance and also calculating the magnification. So image location with ray tracing is a primary skill that you will be assessed on. Can you identify or draw properly the principal rays for a mirror and for lenses when we get to lenses? So I usually do this if I was in the classroom. I would have a meter stick and I would do this on the board, and you would see that magically all of these rays, when you draw them out correctly, they will meet up here. This isn't just something that you see in a textbook. It's actually something you can do on a sheet of paper. So I picked the concave first. This is a concave mirror. What you're going to see here is that we put the focal length on what I call the central axis. This is a central axis. And I abbreviate it with CA for central axis. And you can see that up here. Light leaves the object, and you can see that there's some rays here. Light leaves the object, hits the mirror, and then it meets up here to create the image. And you can see that this is the image. Another point that I want to point out on here is the C. Notice the C on here. C to me is the center of curvature, and I said that up here. Here's the center of curvature. It is 2 times R, right? C equals 2 times R, and that comes from the equation up here. The focal length is half the radius. Well, the radius is twice the focal length. And that's what this is this is the one radius away from the mirror is the center of curvature. So that is on the diagram as well. We can see that there's 3 primary rays on here. I'm looking on here and there's this green one is not a primary ray. The first one is the blue one. It goes in parallel to the central axis and out through the focus. So this is the one that defines the mirror. It goes in parallel, and you just take it to the surface of the mirror. When you get to the surface of the mirror, you reorient your flat edge or your ruler, whatever you're using in order to draw your rays, and then you make that ray just go through the focus and you extend it outward, and that's the first one. The second one in here goes through the focus and out parallel. So that's the red one in here. And I have corresponded it. What these are labeled here are actually what these numbers are. So the red one, if I follow the red one, it goes in. I'm going to line up the tip of the top of my object and line it up with the focal point here. And then just make it hit the mirror. It'll hit the mirror here. And then I send it out parallel. And at that point, you have 2 rays, right? All we need is 2 rays to intersect in order to find the image. So we have the blue one and the red one, and we see they meet up here. The last one, and I think the last one is kind of the easiest one to draw. It's the purple one up here. It leaves the tip of the object, goes through the center of curvature, hits the mirror, and because it's hitting at a 90-degree angle, remember the radius is at a 90-degree angle with the surface of a sphere. Because it's at a 90-degree angle, theta I equals theta R. Well, theta I equals 0 in this situation. So it's going to come in, hit, and then leave at the same angle again. And that's why I think it's one of the easier rays to draw. And you will see that it also goes through the tip of the top of the image. So in order to locate an image, we're going to assume all of the light leaving point P comes in, hits it at a right angle, and we can locate the bottom of the image. And then we can locate the top of the image by tracing rays from the top of the object. And so that will be the image. That's how you find an image for a concave lens with these 3. These 3 rays are going to be the same for the convex lens, but because the focus and the center of curvature are behind the mirror rather than in front of it, we're going to have different rays going in and out. And so number 1 is still the blue ray. It goes in parallel and then out through the focus. Notice it will diverge off this mirror, and I'm going to trace the ray back. I'm going to extend the light ray behind the mirror to the focus. And you're seeing here that it will create that image. Let's follow the red one, number 2. Number 2 goes in as if it were going to go to the focus, all right? But I wouldn't necessarily draw this line on the picture. It's not forming an image. You can see that it's not meeting up with the blue line in order to create the tip of the image. So I draw it in, heading towards the focus, and then it redirects at the surface of the mirror and goes out parallel, in through the focus, out parallel to the central axis. So the reflected rays are the ones that I extend behind the mirror in order to find the image. So you can see that the blue ray and the red ray that's extended behind the mirror, the reflected ones. This is the reflected one. This is the reflected one. Those get extended behind the mirror to create the image. The last one, the purple one, number 3 here, in and out through the center of curvature. Again, you can see that it meets at a perpendicular angle with the mirror. It'll come in and leave along this line, and I will extend it behind the mirror towards the center of curvature, and you can see that meets up with the blue and the red extensions already. So there's the image here for this object. Again, we're assuming P is along the central axis, and I've located the bottom as well. When we look at images, what we like to do is qualitatively describe the image. What does the image look like? And so there's different types of image. Your ray tracing sketches should help with and match up with your calculations. I mentioned that before. So when we're doing this ray tracing, they should all match up with what you calculate in your equations here. The first distinction that we make with images is it real or is it virtual? And in order to do this, I look at the sign of the image distance. You may notice this. This is a concave mirror, and the image is formed behind the mirror. This would be a negative image distance, just like with a flat mirror. A positive image distance is in the case here. I had this example earlier with the concave mirror. I can see that the image forms on the same side as the object. This is a real image. I can see that the light rays, the actual light rays, leave the object, hit the mirror, and they are the actual things that meet up. You would be able to see, this is like a hologram. You would be able to see this image just floating in space, which is kind of weird to think about, but true. As opposed to virtual images, which is the majority of images created by mirrors are virtual images. And I find that students get kind of creeped out or have this definition of virtual in their head that sometimes impedes their understanding of what a virtual image is. So the virtual image here, just to reiterate the definition, is the virtual image, this is a virtual image, is created by extensions of the reflected rays behind the mirror. You can see that the real rays over here, these reflected rays, don't meet up on the real side of the mirror. They meet up on the back side, and this is a virtual image, just with this flat, like with this flat mirror. Other distinctions we can make: is it upright or inverted? You can see in both these situations, these are upright images. We had an upright image here, and that's why we do the tip and the bottom, is then we can figure out, is it upright or inverted? So because it points in the same direction, the image points in the same direction as the object, we're going to have an upright image. I've seen books try to trick students, like they'll do the original object pointing downward, and so then the image will be pointing downward. And so you want to say it's inverted because it's pointing downward, but the inverted refers to relative to the original object. So in this situation that I have down here that I just drew, it's also an upright object because it's in the same direction as the original object. As opposed to here, they're actually inverted. You can see this one's pointing upward. This one is pointing opposite the original, so it'll be an inverted image. So we can look at the sign of the magnification. It turns out if they're pointing in the same direction relative to one another, the magnification will be positive for upright and it will be negative for inverted because HI will be a negative compared to HO. So you can look at the sign of the magnification in order to figure out upright or inverted. And that should correspond with the image that you have in your sketch. If you get an upright image, you should have a positive magnification, and you can tell that it's upright both from the math and from your sketch. Same thing is true for enlarged and reduced. Here we can look at the magnitude of the magnification. What is this value when I actually calculate this number, right? And what we're going to define it as less than 1, it'll be reduced, right? Anything that is 1 to 1 is their original scaling, and that would be here, right? HI equal HO, and the magnification equals 1 in this situation. You get the same height of the image as you do the object. If it's reduced, that fraction will be less than 1, and if it's enlarged, it will be greater than 1. And when you draw these two when you draw your diagrams, you can also look in your diagram to see what your image looks like compared to your math. So I picked an example here, the convex mirror, and I can draw this over here. I like drawing a picture first just to get it going on. There's a convex mirror. I'm going to draw it in the middle of the page here and draw my central axis. And remember that it has a negative focal length, right? If it's a convex mirror, it has a negative focal length. So negative 1/2 r is going to be the focal length. So that's the picture here. It says an object is placed 15 centimeters in front of a convex mirror with a radius of curvature. So this is the radius of a curvature, 26 centimeters. So we know that the focal length is going to be negative half of 26, which is negative 13 centimeters. So I'm going to draw these things on my sketch here. There's a focal length, and I'll put it back here. Focal length, negative 13 centimeters back here. There's an image on the other side. I'm going to put it in here. I'll put this image in here. It's a little bit more than the other one. So there's an image. And I generally use an arrow. That's the basic way. You may see a person, a light bulb, a bottle, whatever, right? But that's what is going on. So what I'm going to do is choose the ray tracing function in my program here. And I'm going to draw the first ray is going to go in parallel, and then it's going to go out coming from the focus. So what I'm going to do is draw another ray in here that goes out from the focus, and so that ray goes in this direction. Okay, so I'll line it up a little bit here. So that's the first ray. It goes in parallel and goes out through the focus. I would draw behind the mirror here. I would draw this a dotted line here. Instead of it being a solid line, this is a dotted line, and then that would remind me that this is the extension of the light ray behind the mirror. Another ray that I'm going to draw is it goes in as if it were going to the focal point. So it only goes that far. It hits the mirror, and then it will go out parallel to the central axis. So what I'm going to do is get this one to go out parallel to the central axis. And so that's the second light ray here. You can see that it's going out parallel to the central axis, and the image is being created in here. That's where the image is going to be. See it right in there. This ray extends to this point. This ray is parallel, extends to this point. I can see that it's within the focal length here. It's behind the mirror. Because of that, I expect a negative image distance. I can see it's upright compared to the original object. So it'll be upright. I'll expect a positive magnification. And I can see it's smaller than the original object. So I'm going to expect that the magnification is less than 1. All of these things should correspond to the math I'm going to do. I could draw the third one in here. You just, the third principal ray, you draw the center of curvature in here, and then you just send a ray back and forth through here, and you can imagine it passing through the same point as the other two already. Where is the image? Let's go ahead and find out where the image is. So I'm going to use the mirror lens equation here. I know the focal length is -13. DO is 15, so I can put that over here. DO equals 15 centimeters. And so I can plug those numbers in, but I'm going to solve for DI first. DI is 1 over the focal length minus 1 over the object distance, and then I'm going to have to take the reciprocal of that when I get done. So I'll go 1 over -13, that's the focal length, minus 1 over DO, which is 15, so I get minus 1 over 15, and then I would invert that. And when you run this through the calculator, you get a negative 6.9643 centimeters. I get a negative sign here, which I expected already. I had drawn the image here, and I can see it's a little bit more than halfway, and that corresponds to the math that I calculated. Okay, so very pleased there. Another thing I'm going to note here as I'm plugging in these numbers is that I didn't convert it to SI. I did not convert to meters. Everything in my equation is in centimeters. I don't mind that my answer is in centimeters, so I'm just going to leave it in centimeters. There's no reason to convert it in this situation. When we do magnification, you can see that's also true. If I do a ratio, even if I convert it to meters, that ratio is going to cancel. That ratio is going to be true whether I multiply by 100 or not. So it asks, so we solved where is the image. We figured out where the image is. Is the image real or virtual? The image is located behind the optical device where the extensions of the rays meet up. So this is a virtual image. We can see that it's upright, and we can also see that it's reduced. I can calculate the magnification. That's the last thing to do here. Calculate the magnification. Magnification, I don't know the image height or object height, so that portion of the equation I can't use. So let's use negative DI over DO. So I'm going to take the negative of the DI that I found, which is negative 6.9643, and divide by DO, which was 15. And I can see when I calculate this, I get a magnification that's a positive value. And so I get positive 0.4643. This does not have any units. It's dimensionless. It's a magnification. It's a ratio of those two heights. It has no units. I see that it's a positive value. I expected that. It's upright, so I get a positive magnification. And then also it's reduced, so I see the magnification is less than 1. So my math corresponds to my picture.